Here's my next example. This is a little bit more complicated. Here, we've got a capacitor, a big one, 1 farad, and a 4 ohm resistor. And we've got a switch. The way I've drawn it, it's going to open at time equals 0. There's another resistor down here. We've got a current source over here. It's a 3 amp. We've got a 1 ohm. And we've got a 3 ohm. And my question is, we've got this current. I'm going to define in this direction. I can define the current in any way I want to. I'm going to define it going down to be different here. And my question is, find the current for all time. First step, well, I guess I got to finish connecting that current source. So our first step is we're going to draw it for time less than 0. And for time less than 0, our goal is to find VC, capital VC naught. And to do that, our capacitor looks like, is it an open or a closed?
Close.
Our capacitor is open. So capacitors look like opens and inductors look like
I'm sorry, I was thinking about the switch.
Oh, yeah, okay. So for time less than 0, right, the switch was closed. And that gives us this. How can we simplify this? And DJ, you had a good insight earlier when you talked about stuff being in parallel. Are there any resistors in series or parallel that will not affect what we're trying to find, which is our VC naught over here?
The 2 ohm and 4 ohm resistors are in parallel.
Exactly. Their tops are both connected, their bottoms are both connected, and so therefore they're in parallel. And it looks like we've got this thing in the middle, but it's connected by a wire. I mean, we could have redrawn this with our current source to the right or to the left, and it would not have changed the topology of the circuit. So we can more simply draw this. And 2 in parallel with 4 is product over sum is 8 over 6 is 4 over 3. And this is 3. And what's your next step?
You can use Ohm's law to find the voltage across the resistor.
Yeah, and you actually did a second step in your head with that. You said, where is my current going? And my current is always flowing in that loop. It's not going anywhere but that loop. So I know I've got 3 amps flowing through this resistor. None of it's going this way because it can't, because there's an open. And so therefore I know what my voltage is across that resistor. It's just 4/3 times 3, which is the same thing as 4 volts. And then the voltage across this resistor is
0.
0. By Ohm's law, since there's no current, there's no pathway for current to flow. So therefore there's no voltage. And so therefore there's 4 volts here, and then there has to be 4 volts here because it hasn't been dropped at all. So therefore there has to be 4 volts here, and our VC naught is equal to 4 volts. So now we can draw the second step, time greater than 0. And in that we want to find REQ. We want to find REQ so that we can find tau is equal to REQ times C. And here we've got this capacitor and the 4. Now the switch is open, so we don't have to draw it. It's not contributing anything. We still have this 3 amp source, and we still have this 1 in series with 3, which is the same as 4. Now, before we get wild about simplifying things, let's remind ourselves what we're trying to find. We're trying to find the impedance seen by that capacitor. And it's still there, but we're going to ask ourselves, how hard is it to push current through here? And in order to do that, we're going to zero out all of our sources. And so the 3 amp source becomes an open. And so now once this becomes an open, we just have, here's our capacitor, and we just have our 4 and this 4 in series. And so our REQ is
8 ohms.
is 8 ohms. And therefore our tau, which is RC, is equal to 8 times 1, or just 8 seconds. Realistically, that's a pretty big capacitor. It's hard to find 1 farad capacitors in the world. All right, third step. Find VC at infinity. And to do that, we'll draw it for time at infinity. So a time at infinity is this switch open or close?
This is the same as the last one.
It's the same as the last one. And now this capacitor really does become an open. Instead of us just drawing it as from its perspective, we can say it's actually in all ways, shapes, and forms indistinguishable from an open circuit.
For this, we don't need to zero out the 3 ohm.
The 3 amp, we can't zero it out
Or, I'm
because
sorry.
we're
Yeah.
not asking what equivalent resistance is. Our goal is to find voltages. So the very first step is to find a voltage. The last step is to find a voltage. Intermediate one is to find that resistance. So our goal again is to find, and you're not alone in that, DJ. I promise you that there'll be a lot of folks who lose track of what they're trying to find, but we're just trying to find that VC of infinity. So I think you've already said it before. Where's the current flowing?
In the right side of the.
It's all flowing in the right side. It can't flow in the left side because there's an open. And so by Ohm's law, that means that the voltage across this 4 ohm on the right is
12.
12 volts. And we know that there's going to be no voltage across this 4 ohm because there can be no current flowing through it. And therefore our V infinity is going to be also 12 volts. And so now we can plug it into that equation, that plug and chug equation, which says that VC is always going to be equal to V of infinity plus V naught minus V of infinity times e to the minus t over tau. So therefore it's equal to 12 plus 4 minus 12, which is minus 8, e to the minus t over 8. But that's not our question. Our question says, what's I of t? So how do we figure out what that is?
We use the equation, where is it at? V equals Li, or I'm sorry, wrong equation. I equals capacitance derivative of voltage.
Exactly. So we'll just multiply this by the capacitance, which is 1 farad, times the derivative of this, and tell me what's the derivative of the first part of the constant?
0.
0, and the derivative of this part?
E to the, or positive e to the t over 8.
That's it.
Yeah.
The 1 over 8, the negative 1 over 8 canceled with a negative 8, and we just get this, and that's in amps. And so now we can write e to the minus t over 8 amps, and that's our answer. Almost. That's our answer for time greater than or equal to 0. What was it for time less than 0? Let's go back to our picture over here for time less than 0. What was the current through the capacitor for time less than 0?
4. Wait, what were you asking for the which one? I'm sorry.
So we want to find the current for all time.
Mm-hmm.
And so to find the current through the capacitor for all time, it really has 2 different time regions. It's got one for time less than 0, and then it's got this e to the minus t over 8 amps that we just figured out for time greater than 0. So what was it for time less than 0? What we're asking again is, what is this current for time less than 0? So what's this current in this circuit?
0.
0. And so now we can write our entire answer, which is
yeah.
which is that. All right. What if I asked something meaner? What if I said
Power.
power? Actually, believe it or not, that's not so bad. If I asked for power, what's the power?
Oh, it's just 1/2
the
capacitance
capacitor.
voltage squared.
That's energy.
Oh, that's
Power,
energy.
power is even easier. Just I times V. You've already
I-
found IC, you found VC, so just multiply them together. Done. Not bad at all. For time less than zero, you're multiplying by a zero, so it'll be zero. And for time greater than zero, it would be whatever this thing is times this thing. Be a little bit of algebra. Wouldn't be too bad. No, I want to find out something meaner. I want to say what is find the voltage across the 3 ohm resistor. How the heck do you do that? For let's just say for time greater than zero. You could easily do it for time less than zero, just looking it over here.
Mhm.
We're talking about that, since there's and that's just a current divider. Some of this 3 amps goes to the left, some of it goes to the right, just by a current divider. You could figure that out. But what is it for time greater than zero? How do you modify? You now know what this current is through the capacitor. You know what the voltage is. You know what the current is through the capacitor, the voltage across the capacitor. What is the voltage across the 3 ohm resistor up here? Take a look at it over here, over in this time region. We want to find the voltage across the.
The current's gonna stay the same, and we have the resistor and the current, so wouldn't it be 9?
Well, let's take a look at it. No longer is it just a 4, right? Now it's a
Mhm.
1 and a 3. But I think you agree that if we could find the current through here, the current through the 4 is the same as the current through the 1 is the same as the current through the 3, right?
Yes.
So if we could just find that current through the 3, I'm going to call this I sub 3, we can easily find the voltage across the 3 ohm. I mean, specifically,
Yeah.
the voltage across the 3 ohm is going to be equal to I sub 3 times 3, just by Ohm's law.
Mhm.
Now, we've already found, though, part of this problem. We've already found what this I is.
It's 0.
Not for time greater than zero, it's not.
Oh wait, I'm sorry. Yeah.
We found it down here,
Yeah.
right? So if you know that there's 3 amps flowing in and there's I sub C flowing out, can you tell me what I sub 3 is?
Oh yeah. So I sub 3 is going to equal. Hold on, I gotta write this down as I write
By
it.
KCL.
Mm-hmm.
Yeah,
It's
let's do it. We've got
entering.
IC flowing out to the left. We've got how much flowing down?
I guess -3.
That's exactly right. And then to the right, we don't know what that is. That's what we'd like to find. It's I sub 3, and that has to be equal to 0. So we can now solve for I sub 3 here. We can say it's equal to 3 minus I sub C, but we already figured out what I sub C is down here. So that would be 3 minus e to the minus t over 8. And now we can find out what V sub 3 is. It's equal to 3 minus e to the minus t over 8, all times 3, what we from up there.
Yes. Okay.
So once you, the point is that once you find what VC is, everything else just sort of falls apart through some sort of mixture of KVL, KCL, doing what you did with taking the derivative, that constitutive relationship between current and voltage. It all just sort of falls apart.
Okay. Yes.
Yeah.
I see.
Yeah. And it doesn't, you're not going to just know it looking at it. It takes believing in yourself that you've got all the information you need, plus your circuits one skills to do something relatively simple. This is the example I just gave is about the most complicated example I could give. And if we wanted to be totally correct about it, if we wanted to find it for all time, this is for time greater than or equal to 0. Do you want to take a stab at it for less than 0?
Yes. So we'll be looking at the first circuit that we drew,
That's right.
and we know that so it's very similar. So we have I
Some of this
leaving.
current comes this way, some of it comes
goes
that way. What would that, let's call this I sub 3 0, 0 for original. Do you remember what the current divider law is?
The current divider.
Because that's what this is. You got 3 amps. Some of it goes to the 4, some of it goes to the 2, how much of it goes through the 4. Do you remember what that is?
No, sir, not the top of my head.
Yeah, so it's like the voltage divider, but the opposite way. So it's still source here, and then it's still the sum, 2 plus 4 in the denominator. But what's in the numerator for the voltage divider, it's the one that you want to find. For the current divider, it's the one you don't want to find.
Oh, I remember this. Okay, yes, I remember.
So what goes on top? You want to find this one, so you're going to put in
2.
the 2.
Yes, I do remember this now that I've seen it.
So now it's 6 over 6, or 1 amp. And let's just do a quick, does that make sense? We've got 1 amp flowing through here. That means if this is 3, we've got 2 amps flowing through this side. Does it make sense that we'll have twice the current flowing through the resistor that's half as big?
Yes.
Yeah, it does. Okay, so we believe this makes sense. And now we can just simply say, therefore, V3 for time less than 0 is going to be equal to I30 times 3 by Ohm's law. So that's 3 volts. And now we can come up with a full V3 that is equal to either 9, whoops, for time less than 0, it's equal to 3. And for time greater than 0, it's this simplified 9 minus 3 e to the minus t over 8 volts for time greater than 0. Ooh, that was a lot.